Right. So let us begin with a brief recap of the last 3 minutes from yesterday, where time was running too fast and I probably made a small misprint at the end. So here is again the Poincaré transformation of a field where we only take the generator corresponding to our index L, to the polarization vector L, which is one of the unphysical polarization vectors. And if we do the right-hand side calculation like we did yesterday, then we get a Poincaré transformation of this L generation or annihilation operator, which gives this matrix connection to the original generators defined at momentum p with polarization lambda. And we get a prefactor from the polarization vector, which is p prime mu. And this p prime we can write as a Lorentz transformation of the original p, and the p we can write as a derivative d mu, which acts on the exponential function here. And the rest is not important, but what it tells us is that this field here, which is coming only from the L generator, transforms into lambda mu mu times the total derivative of some operator expression. And therefore, if we take now our full vector field operator, which we defined yesterday, and we remove the unphysical generators, in particular if we remove the L generator, then that term is of course missing from the Poincaré transformation of that field operator, and therefore what we get is the original one of the full field operator, lambda mu mu times the field A nu physical, minus this thing because we left that out. And that can be again written as lambda mu mu times the derivative d nu of some operator, which is the negative of this square bracket, and we call that omega hat. And so we see that our physical field operator, which consists only of the lambda equal 1 and 2 generators, transforms into two terms. One is covariant, and another term which looks like a gauge transformation. And so this now concludes our section on the summary of the problems that we are now faced with in the quantization of spin 1 massless fields. Namely, on the one hand, we could define an operator field A mu of x, which consists of the 4 different generators, 1, 2, L, and S. That transforms covariantly only into lambda mu mu times itself, so it's a proper 4-vector field operator. However, it contains, of course, the unphysical degrees of freedom, L and S, and they mix via Lorentz transformations. So the physical ones, 1 and 2, they go into S, or the unphysical L goes into 1 and 2. And also, some of those generators in the original basis, the 0 generator, generates a negative norm state in our Fock space. And so the covariant field contains unphysical degrees of freedom, which also have negative norm. So that is for sure a problem. And the other side of the same problem is if we remove the unphysical degrees of freedom and define only such a physical field operator, which contains only the physical lambda 1, 2 degrees of freedom, then the Lorentz transformation of that operator is not covariant. So we violate Lorentz covariance because we get this additional term. Interestingly, the additional term looks like a gauge transformation. So that already tells you that maybe gauge invariance is actually necessary for Lorentz invariance, but anyway, we list here this fact. The extra term looks like a gauge transformation. And so these are the two sides of the same problem, namely Lorentz invariance and quantum mechanical properties like positive norm states and only physical degrees of freedom. They are difficult to reconcile in the case of massless spin 1 particles. And so now, with this in mind, our results from yesterday are summarized, and today we will of course build up a coherent and beautiful, nice framework where all the problems are of course solved. Okay, so let us begin. And now we finally start in our blueprint sort of way with the classical setup. Of a classical field theory, which can be somehow quantized, maybe not exactly in the typical standard canonical way, but which will be quantized. So the theory that we start with is, of course, a theory for a massless vector field. And we know what we need to take. This is the Maxwell theory. L equal minus 1 over 4 F mu nu F mu nu. This is the free Maxwell theory, or the free theory for a massless vector boson. It is the same Lagrangian as for the massive field, only the mass has been set to 0. And here, again, the field strength tensor is given by this antisymmetric combination of derivatives of the 4-vector field. Good. And so we know that this combination is a combination where we get constraints, and we know that we need constraints in our classical theory in order to reduce the number of degrees of freedom. Let us look at the conjugate canonical momenta pi that result here from this Lagrangian. Pi mu is defined as the derivative of the Lagrangian with respect to a mu dot. And that is the same as in the massive case, because the mass does not play a role in the definition of the canonical momenta, and so we know what the result is. The result is F mu 0, the field strength tensor with its index structure. And so again, this is 0 for one of them, and Fi 0 in the other cases. So the canonical momentum pi 0 identically vanishes, which is of course a constraint. And we had the same constraint in the massive case. Then the equation of motion. The equation of motion is the free Maxwell equation without sources. And what is the equation of motion? It is of course simply d mu F mu nu equals 0. And we can, for the record, explicitly write that down by evaluating the field strength tensor. Then we get here D'Alembert acting on a nu minus d nu acting on d mu a mu equals 0. These are the two ways to write the equation of motion. And the Proctor equation was similar. The Proctor equation for the massive case contained here also a mass term on the right-hand side. And that mass term could be used, for example, to get additional information, a corollary as we called it, on this d mu a mu. In fact, we could prove that d mu a mu was 0. Now we cannot prove that because the mass term doesn't exist, and in fact this d mu a mu does not have to be 0. So these are the equations of motion, and it is always, if we have constraints, good to look what happens to the constraints in the context of the equation of motion. And here we see that this here for the different, for nu equals 0, for nu equals 0, we have here the canonical momentum appearing. So for nu equals 0, we simply have di pi I equal to 0, right? For nu equals 0, we get this equation, literally di pi I equals 0. And that is also a constraint, because it's an equation of motion which does not contain the time derivative. Anything where you get a relationship between canonical variables without time derivative, that is a constraint. And so we have actually two constraints, namely pi 0 has to vanish and di pi I also has to vanish. These are two constraints. How many constraints did we have in the massive case? Who knows it still? We also had two constraints because there was a similar equation like this one. However, that equation involved the mass term and it involved the A0 field. There was a constraint involving the A0 component. And that is where the difference comes from between the massive and the massless case. In the massive case, we had here A0. Here we had pi 0, so we had two constraints, one of them for pi 0, one of them for A0. The Poisson bracket between the two constraints did not vanish. That means the constraints were of second class, which is the simpler kind of constraints. Here, there is no A0 appearing. We only have the pi's in the constraints, and therefore the Poisson bracket between the two constraints vanishes, and we have this first class constraints which corresponds to gauge invariance. Two constraints of first class. So we have gauge invariance. And of course, that is not a surprise for you, because you know that Maxwell theory is gauge invariant, and so let us make that explicit. What is the gauge invariance of this Lagrangian? The gauge transformation is A mu of x goes to itself, A mu of x plus a derivative d mu of some arbitrary function alpha of x. And under this gauge transformation, the field strength tensor, what does it do? It stays constant. So the field strength tensor is gauge invariant, and therefore also the Lagrangian is gauge invariant. Okay. So this is the gauge invariance of the Maxwell theory. Very simple kind of gauge invariance, but leading to highly non-trivial effects. And that is expressed here in this more abstract way via constraints. So the physical meaning of such a gauge invariance is always that there is no unique solution to the equations of motion. Remember our first or second lecture where we had an example of such a case. And what it simply means is that for each initial via constraints. So the physical meaning of such a gauge invariance is always that there is no unique solution to the equations of motion. Remember our first or second lecture where we had an example of such a case. And what it simply means is that for each initial condition, so if you impose an initial condition on your field at some instant of time, you impose initial conditions on the field and also on the time derivatives of the field as much as you can possibly do, then still there are infinitely many different solutions to the equations of motion. So clearly all of those infinitely many solutions must describe equivalent physics. So in a gauge invariant theory, we have this situation that you have infinitely many solutions to equations of motions which form an equivalence class which describes just one set of physical of physical situations. And so also in this case that we also learned in our example in the first or second lecture, the transition to the Hamiltonian and to Poisson brackets is more difficult. For example, for our case in the lecture at the time, where we had simply this single particle, if you remember, a single particle which was measured by a ruler which could move. So we had a Lagrangian which only depended on Q1 minus Q0 square, and so that corresponded to a ruler which is moving, and you describe trajectories of the particle relative to this moving ruler. And of course the movement of the ruler is completely unphysical, and that corresponds to this simple gauge invariance. And then we could go to a Hamiltonian, but there are infinitely many different Hamiltonians which are possible, and each of those infinitely many Hamiltonians would give rise to one example solution to the equation of motion. So there is an ambiguity in going to the Hamiltonian picture, and that is simply what I mean by saying it is more complicated, and the general case you can find again in this book by Renaud Teitelbaum, which develops an entire formalism just to solve this problem in complete generality. But we don't have to solve it here in complete generality. What we want is one quantum theory corresponding to that classical theory. And so for this we need to make a choice of the gauge. We need to make a choice of gauge, and there are different choices that one can make representing some subset of the possible solutions to the equation of motion. And which choices there are, you already know from classical electrodynamics, where in the lecture you typically also discuss several different gauge choices, each of which have different advantages. Very well-known choices of gauge. One of them is the so-called Coulomb gauge. If you use the Coulomb gauge, you require that in three-dimensional notation, nabla A vanishes, or in our notation, DI, AI vanishes. Okay, so this is a non-relativistic gauge choice which is often very useful in static situations like static magnetostatics, but also in some electrodynamical situations. Anyway, the equation here simplifies a little bit, and in particular if you now look at the equation for the A0 potential, the A0 equation for nu equals 0 here becomes now simple, because here the spatial part drops out, and what remains is here for A0 the double time derivative, but also here you have a double time derivative of A0, so the double time derivative drops out, and what simply results is you get these equations Laplace of A0 equal 0. Very simple equation for A0, but even if you would have sources, charges and currents, then you would have here not 0 but charges and currents on the right hand side. In that case you would get simply something proportional to the charge density. And that tells you that the equation of motion for A0 in Coulomb gauge does not involve a time derivative again. So A0 can be just solved instantaneously by the charge density. So that is a kind of equation of motion and a solution which seems to violate causality, because it means that the A0 field here is influenced by the charges everywhere else in space at the same time, which is a non-relativistic kind of dependence. It is a dependence which seems to violate causality, and causality is only compatible with this because the A0 is of course unphysical. It's a gauge-dependent quantity, and if you now compute gauge-independent electric and magnetic fields from this, then one will see that causality is restored. But I mean, that is the outcome of this non-relativistic Coulomb gauge choice, that you get this causality violating equation of motion, which is however simple, and therefore it's nice to use it in some physics applications. Another choice is the Lorentz gauge, which of course has this extremely funny name because it's Lorentz gauge, which is Lorentz covariant, but it was not invented by the Lorentz which invented Lorentz invariance, but by the other Lorentz without T in the name. So it's Lorentz gauge, which is this. So d mu a mu equals 0, so that is a Lorentz covariant gauge, and in this gauge we get the equation of motion, which is even simpler. So now that term is 0, like in the massive case, but that is now the Lorentz gauge choice, and we get as equation of motion simply this. So that is a very nice relativistically invariant gauge choice, and then also relativistically invariant equation of motion. So it's a Lorentz covariant gauge. Then we will mainly try to work in a Lorentz covariant way. So for us, the second kind of gauge choice is now preferable, at least for today. And on Thursday I will make some remarks on Coulomb gauge, but let us focus today on Lorentz invariant or covariant gauges. And then we can actually write down a modified theory, namely a modified theory where the Lagrangian equation of motion gives directly this equation, which is the equation of motion in our Lorentz gauge choice. Okay, so now we know that this is the equation of motion that we want in this gauge, and we ask ourselves which Lagrangian gives rise to this equation of motion, and that will give us a covariant Lagrangian with so-called gauge fixing. And I will tell you directly the answer. The original Lagrangian and then this so-called gauge fixing term, which looks like this, minus 1 over 2 psi times d mu a mu squared. And so you see, first of all, our gauge fixing term here contains a free parameter, which gives us some freedom. And physics in the end should be independent of that free parameter psi. So if we keep it free, then we can check the independence of physical results on that parameter at the end of calculations. And the term is multiplied with this d mu a mu square, which is of course Lorentz invariant, and in Lorentz gauge that term would be 0. So that is our ansatz, and now let us study what it leads to. The equation of motion is now the following: 0 is equal to d mu f mu nu from here, and then the derivative of that term here gives the following: plus 1 over psi times d mu G mu nu times d rho a rho. So from the usual derivative, when deriving Euler-Lagrange, the 1/2 is of course cancelled, and one of these factors here remains, and the other factor needs to be taken derivative with respect to d mu a nu. And if you take the derivative of that with respect to d mu a nu, you simply get the metric tensor g mu nu. And that d mu comes from the Euler-Lagrange equation. So, and if we just plug in the definition of f mu nu, then we get here D'Alembert a nu minus the other term, and the other term is the same as this term. The other term is d, as it is written here, the other term is d mu a mu, and this is also d nu d rho a rho, so these two terms are the same, and so therefore we get minus 1 minus 1 over psi times d mu a mu. So therefore, if the Lorentz gauge condition holds, this equation of motion is equivalent to Maxwell. Right? Because the additional term is d mu a mu. This term is modified. In the original Maxwell equation, we have at the top left, we have coefficient 1. Here we have modified the coefficient, but this term is anyway 0 in Lorentz gauge, and therefore the change of the coefficient doesn't matter. So if the Lorentz gauge is satisfied, the two equations are equivalent. And they are both equivalent to this equation, simply D'Alembert a nu equals 0. So therefore we have now written a Lagrangian which is equivalent in our Lorentz gauge, and the advantage of this Lagrangian is that it has no constraints anymore, and therefore we can immediately quantize it, no problem at all. We just need to look at the pi's. Pi mu is now the derivative of the Lagrangian with respect to the time derivative of a mu. And so then from here we get, of course, first of all, f mu 0, which is a problem for mu equals 0, because it would vanish. But then we get the additional term, and the additional term is minus 1 over psi times metric tensor g mu 0 times d mu a mu. Okay, and so if mu is 0, then that vanishes, but this does not vanish, and then we get a non-vanishing canonical momentum for a 0, which also contains a time derivative of a 0, so that is all perfectly normal situation. And if mu is non-zero, we get the original canonical momentum. So all the canonical momenta are now perfectly well defined. They are all non-zero, and they all involve the time derivatives of the original fields. So there are no constraints. And therefore, this Lagrangian, which is equivalent in Lorentz gauge, has no constraints and will be perfectly easy to quantize. Okay, therefore, let us quantize it. Let us now look at the quantization of this system here. Or are there any questions to the classical theory before we start the quantization? Any questions? Okay.
Yes.
Yeah.
What if we set psi equal to 1?
That is the simplest case, which we will later also choose. In the psi equal 1 case, this term completely drops out, and we immediately recover that simplified equation of motion, which we get in Lorentz gauge. Right, so psi equal 1 is really the simplest choice for psi, So if you want to make your life as simple as possible, then you choose psi equal 1. But for other values of psi, it still is true that these equations here are equivalent to Maxwell if we also have Lorentz gauge. And so we will actually now choose psi equal to 1, because then the quantization is much easier, and the Lagrangian is easier, simpler, and the equation of motion is simpler, so everything is much simpler for psi equal 1, and that is the only thing we will use here in the lecture for the quantization. But you can do all the subsequent steps also for other values of psi, and you can define the quantum theory for all values of psi, and as I mentioned, it must be true at the end that physical results for amplitudes, for matrix elements, for cross-sections and so on, they should be independent of the value of psi. So it's actually useful to carry out some explicit calculations for arbitrary psi in order to be able to have a check of your calculation really makes sense, that it is gauge independent. But psi equal 1 is the simplest choice. Maybe it's not so obvious, but there is another choice which is also very useful and which is not maybe obviously simple, but which is simple, namely psi equal to 0. If you choose psi equal to 0, then you get something called Landau gauge. Of course, then the term here diverges. So it's not obviously possible to take psi to 0 in the Lagrangian, but in other expressions you can take psi to 0, and that is then also a very nice simplification. But we will use psi equal to 1. And then we can perform a covariant quantization, which means a quantization which is at all steps of the procedure compatible with Poincaré transformations. So we take our gauge fixed Lagrangian, which is indeed Lorentz invariant, and we first ignore the Lorentz gauge condition, but which is d mu a mu equals 0, but we remember it later. But for the time being, we forget about it and simply look at the Lagrangian as it stands in the box and quantize it, because then we know it's perfectly possible to quantize this Lagrangian, and as we just mentioned, we nevertheless make our life even easier by choosing psi equal to 1. And I refer again to this long review by Nakanishi from around 1972 for the general case. And a little bit of the general case is also given in the field quantization book by Greiner. All right, so for psi equal 1, our Lagrangian actually simplifies. We discussed that already last week or 2 weeks ago. The two terms coming from the f mu and this d mu a mu square term. We had at one point in the lecture, some of you made some suggestions for Lorentz invariant Lagrangians. We had some ABC coefficients which were linearly dependent. And actually, this d mu a mu square corresponds to what we called C coefficient at the time, which cancels some terms in the f mu. So this Lagrangian is simply equivalent to 1/2 d mu a mu times d mu a nu, just like that. All the other terms here drop out after partial integration. And so this Lagrangian now is still obviously Lorentz invariant. It contains derivatives d mu in this symmetric fashion. It contains a field a nu here. So if you consider for a moment just one index nu, let's forget about the index, then how does it look like? d mu a that is identical to the Lagrangian for a scalar field, to the Klein-Gordon Lagrangian for a scalar field. And actually what this is it is a Klein-Gordon Lagrangian for 4 different fields, namely for each A nu, for each index nu. It's a Klein-Gordon Lagrangian. So that is simply a sum of 4 Klein-Gordon Lagrangians for 4 fields A nu. What about the sign, however? The sign in front is minus, and then we have here this sum over nu up and down. So that means for nu equals 0, the metric tensor is 1, and then for nu equals 0, we have here minus a Klein-Gordon Lagrangian, so we have the other sign. But for the spatial indices I, we get a minus from the metric tensor, and then for the spatial indices, we have in fact the normal correct sign of a Klein-Gordon Lagrangian. So 3 times the correct sign and 1 times the wrong sign. Wrong sign for A0. Okay, but anyway, regardless of the wrong sign, it is now clear what happens. So every of these fields A nu satisfies the Maxwell equation, which is a simpler in Lorentz gauge, and this is actually the Klein-Gordon equation. It's the massless Klein-Gordon equation, D'Alembert A nu equals 0. It's the massless Klein-Gordon equation. And what about the canonical momenta? Pi mu, the canonical momenta, they become also very simple. Okay, you can take this formula and evaluate it, but a much more direct way is to see that for each field you have a Klein-Gordon Lagrangian. Therefore, the derivative of this with respect to A nu dot is just A nu dot with a minus A mu dot, which is again the same thing as for Klein-Gordon. Therefore, we can say the quantization is obvious. Which is why, in this case today, we will really not go through all the detailed steps, because that is too simple and we have done it too many times. So we can directly jump to the results because we clearly know what the results are going to be. What are the results? The result will be that for each component nu, we get a field which has the same structure as a Klein-Gordon field operator from the quantization, and we can summarize the 4 components in this way. A mu hat of x is a dp tilde integral, and we can write the 4 components nevertheless as a sum over polarization vectors lambda from 0 to 3, which is just a basis transformation, and then we have here epsilon mu of p comma lambda times creation annihilation operators A of p comma lambda times e to the minus ipx plus the Hermitian conjugate of the same thing. And this epsilon mu could also be written as a 4-component object with 4 different A's, but as you know, for specific momenta, the epsilons are just the unit vectors, and therefore this is completely equivalent to simply saying we have 1 independent creation annihilation operator in each component. But it's nicer later to write it in this equivalent form. So in this lambda equal 0, 1, 2, 3 basis, what I just said is true in particular. The epsilons are essentially just unit vectors, and the different A's for the 4 different lambdas correspond to creation annihilation operators for the 4 different components of the field operator. And therefore, each of them behaves like a Klein-Gordon or a scalar field creation annihilation operator. And therefore, we can immediately see, obviously, what are the commutation relations. So A with A gives 0, but we have 4 different A's. So we have A of P lambda, A of P prime, lambda prime. They all commute. They behave like 4 different scalar field creation operators, but we have also A and A dagger, and then P comma lambda, P prime comma lambda prime. And so for different lambdas we get 0. For different lambdas we get 0, but we also get here an impact of the wrong sign. So the A0 has the wrong sign in the Lagrangian, and that leads here at this point to the wrong sign on the right hand side of the commutator, and therefore we can write the prefactor as minus G lambda lambda prime. So for the 0 component we get minus, and for all the other components we get the usual plus. And then we have here of course the usual 2 pi cube times 2p0 times a 3-dimensional delta function of p minus p prime. But the interesting new point is this metric tensor. And of course we already estimated that this would be the result because of Lorentz covariance if we have such a 4-vector field operator. Then again, in the completely obvious way, identically to Klein-Gordon, we define the Hamiltonian, and we can define and compute automatically the commutation relation of the Hamiltonian with our generators, and we get plus P0 times any generator, and here there is always plus because the negative sign in the Lagrangian doesn't affect the commutation relation with the Hamiltonian. Okay, so this is the obvious result, and so it's kind of normal except the wrong sign for one of the creation and annihilation operators, and this holds for the lambda 0, 1, 2, 3 basis. Let me also give you some information on the lambda equal 1 to ls basis, which is just a basis transformation. So you remember here the 0 polarization vector was just this vector 1, 0, and the 3 was this polarization vector, and so what we call here L is the sum of the 2 polarization vectors. So L is the sum of 0 and 3. S is the difference between 0 and 3 vectors, and so if you do a basis transformation of this linear combination here, you get the relationship for the operators, which is the same. So A of S is then A of 0 minus A of 3 divided by 2 for normalization, and A of L is A of 0 plus A of 3 divided by 2. So this is the relationship between the 2 basis choices. And actually in many textbooks, honestly speaking, in all textbooks that I have found, they don't use this basis. I don't know why, because it's much nicer to use that basis. However, I've actually seen nobody using this basis. Everybody seems to use only the 0 and 3 basis, and therefore in many textbooks you see always this combination A0 minus A3 appearing, and whenever you see that, you know that they are actually talking about this scalar operator A of S. So this is what obviously follows. And now we need to start drawing conclusions. the first conclusion is on the resulting Fock space. What is the resulting Fock space that we get? As I told you many times, you need to construct the operators. Operators need to act on some well-defined space, some Hilbert space preferably. And here we need to define the Fock space on which those operators act. As usual, we need to start with a vacuum state, vacuum, which is defined by A on the vacuum gives 0 for all the A's. Then we define one particle states, P comma lambda, defined by acting with a dagger of P comma lambda onto the vacuum state. And so for each momentum, there are 4 linearly independent such one particle states. And then, of course, we get also multi-particle states in the obvious way. And so the problem is that some states have negative norm. Which states have negative norm? The states with lambda equals 0, they have negative norm because, of course, the obvious wrong sign on the right-hand side of the commutation relation. P comma 0 have negative norm. And so now we have already guessed it, estimated it, but now we see it explicitly. That is the outcome of the quantization of our Lorentz invariant Lagrangian on the blackboard. This automatically leads to states with negative norm. And so the basic problem is that we have this wrong combination of signs appearing. So here in this relationship we have a minus, in the other relationship with the Hamiltonian we have a plus. And that is this kind of combination that we cannot correct by, for example, swapping the interpretation of A and A dagger. Because that is something that you can try. Sometimes swapping A and A dagger simply solves the problem, but here the relative sign is such that you cannot solve the problem by swapping some interpretations. And of course, in the Dirac case, we solved a similar problem by going to Fermi statistics, but we cannot go to Fermi statistics here because, of course, for the other 3 polarizations, the behavior is correct. And so the majority of the cases here has the correct behavior, and we have one case with incorrect behavior, and of course we cannot choose a different statistics just for this polarization. That would be inconsistent here. And therefore there must be another solution for this negative norm problem here. Let me write down for you, what do I want to write down? Yes, let me write down an equivalent relationship for our polarizations LS, just that you see it. So for this L and S, what happens is the following, simply generically without momentum arguments. If you do S with S, what happens? S with S gives here this commutator. Imagine you would do a commutator of S, AS with a dagger of S. Then you get one term coming from the commutator of A0 and another one from A3. A0 has negative norm, A3 has positive norm. If you add up the 2, you get exactly 0. So any scalar product between 2 S states gives 0. So they have all 0 norm. They have 0 norm. And they are also orthogonal. With different P, they are orthogonal. But even if you have the same P here, you get a 0 norm state. The same with L. Also gives 0 because of the same cancellation. But if you do S with L, then you get something which is negative, because S with L, and from such commutation relations you would get A with A dagger gives minus, and minus A3 with A3 gives also minus, and so you get something negative here. And so that is an indefinite norm. So and all of that exists in our space of states. We have states with negative norm, we have states with zero norm, but the states are not zero states. They are non-trivial states, but the norm of them is zero, and we have such scalar products. Yes? We have done this exercise for the harmonic oscillator, where you have certain cases of A and A dagger commutation relations between A and A dagger and between the Hamiltonian and A dagger. Both of these relations need to be looked at simultaneously, and for the three other cases with the other lambdas, the signs in those relations are the ones that we discussed in the harmonic oscillator case, which gives rise to a correct Hilbert space if you start out with a vacuum in this way, and then you build up such states, they will have positive norm and positive energy. And so that is how we need to start. For the A dagger, you have now anyway a problem, and that is shown by our analysis. So if we do not go to Fermi statistics, which we cannot do because of the physical polarizations which need to behave like this, so we stay in bosonic statistics, and then our harmonic oscillator discussion shows us that we have one problem. We either run into negative norm states with positive energy, or we run into negative energy states with positive norm. And the two problems are interchangeable, but we cannot avoid that we have one of the two problems. And so in that sense, it would be kind of arbitrary to make one choice, but anyway, both choices are bad. They lead to a Hilbert space or a space of states which cannot be interpreted physically. And we need to solve this interpretation problem later on. And so here, that is what I meant before. You can swap the interpretation of A and A dagger. If you swap the interpretation of A and A dagger and you tentatively try this condition for the vacuum, at least for the zero polarization, you could try it. Then the norm of those states would maybe be positive, but the states would have negative energy, and so you would not entirely solve the problem. And so in that sense, it is a conventional choice that we do this one also for the polarization, and we choose out of the two problems to have the problem with negative norm, which is maybe a little bit more Lorentz covariant, because we already saw that Lorentz covariance probably requires us to have something like this, where we have states with positive and negative norms simultaneously. So this is the obvious thing which is motivated by Lorentz invariance, and so therefore we make this choice instead of the other one. But anyway, both choices would be bad, and we would have to do some interpretation. And so that is now what we want to do. But before going to the interpretation, let me write down the last point. Namely, I said the quantization is obvious, and we just write down the obvious results. And one of our obvious results is not only the commutation relations, the Fock space, but also the Poincaré generators. Of course, you can now also again define P mu, J mu nu operators, and you can define a representation of the Poincaré group on this space of states with the correct commutation relations and the correct representation properties. And this satisfies the properties of our section 263, which is the one from yesterday, where we already assumed what I wrote down on the blackboard at the beginning of today, namely our field operator a mu hat of x behaves under Poincaré transformations u dagger and u in the obvious way. Namely, u dagger a mu times u gives essentially lambda mu nu times a mu. So our field operator is a 4-vector field operator. And therefore we also get the interpretation that those two states, p and lambda equal 1 and 2, we discussed them yesterday already. They have exactly the properties from yesterday. They are physical states with helicity plus minus 1 of a massless spin 1 particle. Massless helicity plus minus 1 states. So they are physical. So if our goal is to describe physical spin 1 massless particles, then those states do the job. They have exactly the correct properties for that. However, the additional states with the polarization 0 and 3 or L and S, they are unphysical. Yesterday we have already seen that the polarization S would correspond to a spin 0 state, but not a normal spin 0 state, but a spin 0 state with 0 norm states. So that can also not be interpreted, and the L has no interpretation so far at all. But these additional states, they serve the purpose of making our field operator a mu Lorentz covariant. If we leave them out, then our field operator is not covariant anymore. So that was the difficulty that we are facing. Yes?
You said the operator for the L doesn't have a interpretation so far. Is there some idea? And also that the S form behaves like a spin 0 particle?
Yeah, that is what we showed yesterday.
But is that really an interpretation? I mean, the states that form 0?
Well, okay, you might or might not like the interpretation, and we shouldn't take it too far in interpreting deeply this thing, because they are not physical spin 0 states. They are unphysical, but if anything, they would correspond to spin 0, because that corresponds to the S polarization. That is really a Lorentz invariant or a scalar field. It's a scalar field, and also in the quantum theory that behaves like a scalar field operator. So its transformation properties under rotations give rise to states which have spin 0. So they would be eigenstates of spin with eigenvalue 0. However, they are not physical states because they have not positive norm. Therefore, I mean, they have a nice spin interpretation, but they have no physical interpretation. So I wouldn't take it too far. And for the L, I do not know any kind of direct interpretation like this. Yes.
So this question
what changes is that the structure of the A mu field operator in terms of A's and A daggers, and the commutation relations between the A's and A daggers, they also change a little bit. But what does not change is the number of physical and unphysical degrees of freedom. We will always get a space of states where we have two physical polarizations, lambda equal 1 and 2, and the rest will be unphysical in some form or another. And the way these unphysical degrees of freedoms behave becomes more complicated if psi is not equal to 1. But the number is the same. Yeah, so we need to come back to this Lorentz gauge condition where that should vanish. And that is actually one of the next steps. where we recall that we actually imposed that condition on the classical level, and we should check what has happened to it on the quantum level. Other questions? Yeah. So then let us go to this point. Maybe let me clean a little bit more. So this is what is it? Section 267. The solution is the so-called Gupta-Euler formalism. Which we now discuss. And first we do what you just remembered, namely we remember the Lorentz gauge condition d mu a mu equals 0. What happened to it? Actually, you can write down the following thing, namely a commutator between A0 and the Lorentz gauge condition. So, because we have now an operator A mu hat, so we can write down d mu A mu hat, but we can also study its commutator with A0, because why not? But actually, what is the result of this commutator? If we just plug in the result from the previous blackboard, then you see that those fields satisfy the canonical commutation relations. And here, among the terms, there is one term which contains A0 dot. This is a sum with A0 dot. The other terms do not contribute, but we get in the end a commutator between A0 and A0 dot. And that is of course not 0, because A0 dot is up to a sign. It's the canonical momentum for A0, and we have canonical commutation relations. Therefore, this thing gives a delta function, but not 0. If the commutator with an operator is not 0, the operator cannot be 0. Therefore, you know the Lorentz gauge condition has been destroyed by our quantization. Canonical quantization has destroyed our Lorentz gauge condition. It is definitely not valid. So let's write this down. A Lorentz gauge d mu a hat is invalid for the operator. That is certainly a problem. And we have other problems which we already know extremely well, because we have mentioned them at least 20 times. We have in our Hilbert space negative norm. And we have too many degrees of freedom. We have unphysical degrees of freedom, which we cannot interpret. So these are three problems, and now all of them will be simultaneously solved by this brilliant idea from Gupta-Euler. And what is the key idea? The key idea is an idea that you should now understand and already have yourself, because we started with this yesterday. We need to go to equivalence classes. We need to define equivalence classes, because that was our way to reduce a four-dimensional space covariantly to a two-dimensional physical subspace. And that is exactly what happens now here as well. We will define equivalence classes of quantum states, and those equivalence classes of quantum states will solve all these problems at the same time. So let me write this down nicely. So what is the key idea? Solve all problems simultaneously by defining the following thing. We define a physical Hilbert space, which we will call curly H physical, And this physical Hilbert space is a quotient space of some space which I call V physical divided by another space which I call Vs. And then those equivalence classes get rid of all problems at the same time. So let us spell out the idea in detail. First, let us define our space of physical states, which I call curly V physical. That is a subspace of our Fock space. So our Fock space is the full vector space of all states in our theory. Sometimes I call it Hilbert space, but it's not a mathematical Hilbert space because it doesn't have positive norm, but it's a vector space where we define inner products and so on, and operators can act on that space. And now we define a subspace of physical states psi, which have the following property, namely they are annihilated by all the AS. Okay, so maybe let me do it once more explicitly. They are annihilated by A of P comma S for all P. And later we might just write they are annihilated by A of S. So they are annihilated by the scalar annihilation operators. If that is the case, then we have already immediately a nice consequence. Namely, the nice consequence is the following. If you look at two such physical states, and you now look at the Lorentz gauge condition, what is now the result? Small calculation from you. Because what is essentially the result of d mu a mu? We had it here maybe 20 minutes ago on the blackboard in the expansion in terms of A and A dagger. Okay, I will give you a few moments to think about this, because you should really be able to understand this point. Exactly. So everybody understands this point. We had it here on the blackboard a few moments ago. Exactly, the expansion of this contains only AS. So it's essentially this up to Fourier coefficients and stuff like that. And why? Because the polarization vectors epsilon, they get multiplied with the momentum. And the only epsilon which does not vanish when you multiply with the momentum is the S. That was the definition of the S polarization. And we already said it yesterday, so it repeats itself over and over again. So I also said this is a scalar field operator. That's what we said 20 minutes ago. It's a scalar field operator which behaves like a scalar field under Lorentz. It contains only S, and therefore this AS stands for scalar field. This is really like the generation operator for a scalar field. So that's why here only AS and A dagger S appears, and that is then zero, because the physical states are defined such that A annihilates this state and A dagger annihilates that state. Therefore now we get zero. So our physical space is defined such that in scalar products or in matrix elements between physical states, the Lorentz gauge is satisfied. So the Lorentz gauge is not satisfied as an operator identity, but it is now satisfied in matrix elements between physical states. That is what we can do, and so Gupta-Bleuler had this idea that that could be an interesting space to consider. It's maybe the most physical subspace that we can define. And so let us now go on. Let us now define equivalence classes. And our equivalence classes are defined by a state that I call Vs. We will then divide by this Vs. In other words, we will define equivalence classes corresponding to it. And those are the following states which have the form, let's call it like this. It's the state space spanned by all states of the form a dagger of p, s acting on psi, where psi is a physical state. Okay, so you take a physical state and act on it with a dagger of s, then you get some state. And of course you can take any value of p or do linear combinations of such states. That's why I say the states spanned by such vectors. And that is a space. And actually this space is a subspace of the physical space. Why is this a subspace of the physical space? Because the commutator of AS with a dagger of S vanishes. That's what I mentioned before. And in case you don't remember, so if you really want to calculate, this is A0 plus A3, minus, and again A0 minus A3, and then you get a dagger. One commutator from A0 with a dagger 0 gives minus, A3 with A3 dagger gives plus, and the two terms cancel, they add up to 0. Therefore this commutator is 0, and if the commutator is 0, then you ask A of S acting on this state, what does it give? You do the commutator, they commute, then you have a dagger times A on psi gives 0. Therefore this state is also annihilated by A of S. And so therefore Vs is a subspace of the physical space. But it's really a proper subspace. Not all physical states are contained in this Vs. And then we say an equivalence class, so two states, psi and psi prime, are equivalent in the same equivalence class if and only if the difference psi prime minus psi is an element of this Vs. So if two states differ by a dagger S acting on something, they are called equivalent. And then we can finally define our physical Hilbert space, which is a state of equivalence classes. H physical is indeed what I already announced, this V physical divided by Vs. And just to be explicit, what does this state contain? What does this space contain? It's a space of equivalence classes. It's a space of equivalence classes that we can call like this, bracket psi, such that, first of all, a representative satisfies A of S acting on psi equals 0. That means that this psi is first of all physical, and on the other hand, that the whole equivalence classes is given by this particular representative plus any state in this Vs. And so we have now defined a quantum theory where the states are actually equivalence classes of states. Now, for the rest of the time today, I want to illustrate this and give you some examples of states which live in this space, and to discuss properties of operators acting on that space. And then we will continue on Thursday, maybe half an hour more, on wrapping up the whole theory. Let me begin with a few examples. Example elements or example states that you can now discuss. So one simple example is the zero vector. So every vector space contains a zero vector. And what is here the zero vector equivalence class is simply this space Vs. So this equivalence class corresponding to the zero vector is the entire space Vs. In other words, you can say it in the opposite way. Every state here, every state which has that form a dagger on something is equivalent to the zero vector. That's the way to look at this. And so that is why also all the elements of this Vs space, they are of course unphysical, they have no meaning. They are now made equivalent to the zero vector. Then we have the vacuum equivalence class. The vacuum equivalence class is of course an element of our physical Hilbert space, because the vacuum is physical. It's annihilated by A of S, so it's a physical state in our definition, and this equivalence class is then one element of this H physical. Then, now that is quite important, so let me use some space for it. What are actually our one particle states? Let us discuss our four different types of one particle states. First, one particle state with lambda equal 1, 2. Then the one with lambda equal S. And finally, the one with lambda equal L. So what are the properties of those states? These states here, are they physical or not? They are physical because they are annihilated by A of S. So they are of course obtained by a dagger of lambda. So annihilated by A of S, so they are physical. And so if we take an equivalence class, then this is of course a physical equivalence class. So these are, for lambda equal 1 and 2, they are not in the same equivalence class, because the difference between the two is not created by a dagger of S. So of course they, lambda 1 and 2 are two linearly independent elements of this physical Hilbert space. So clearly we have two physical degrees of freedom in this space. Now what about this? Lambda equal S. Physical or unphysical, according to our definition here? In which space does that live? And why in this formalism? It actually is annihilated by A of S, and it's actually a dagger on the vacuum, right? A dagger of S on the vacuum. So therefore, in which space, first of all, does it live? It's given by a dagger onto the vacuum. So it lives in the space Vs. In Vs, right? So it lives in Vs, and therefore it is unphysical, because what did we say about every state in Vs? Every state in Vs is equivalent to the zero vector. So they are equivalent to the zero vector, so they are nothing. So this is element Vs, and that simply tells us that this equivalence class here, the equivalence class of that state, is the same equivalence class as this of the zero vector. This is unphysical since it is equivalent to zero, and when I write zero, I mean this zero vector in our vector space. And so you were saying it's not annihilated by A of S, but actually it is annihilated by A of S. You were probably thinking, okay, A of S doesn't annihilate it because of this usual A and A dagger commutation relation like with harmonic oscillator. But here, the tricky thing, A and A dagger of S commute, different from harmonic oscillator. This is this indefinite metric that we have here. So the S and L polarizations, they have these strange commutation relations. So therefore it is annihilated by A of S. So it's an element of the physical space, but it's also an element of the simpler VS space, and therefore it's equivalent to the zero vector. And now what about lambda equals L? Lambda equals L, that, now your answer is correct if you repeat it. This is not annihilated by A of S because of this symplectic kind of metric. So this is not an element of the physical, and therefore it is also unphysical. And let's just remember A of S commutator with A dagger of L, that is not zero. So, two linearly independent physical degrees of freedom and two unphysical ones for two different reasons. The S is unphysical because it's equivalent to the zero vector, and the L is unphysical because it's just from the beginning not an element of our physical space. And so we have this hierarchy of spaces and different ways to eliminate different states. This is how the theory is constructed.
طيب أنا أعتقد أن ال L هنا طبعا هو combination بين 1 2 وأيضا ال L يعطينا كما رأينا الفيديو السابق يعطينا 1 2 وبالتالي تعطينا يعني زبين 1 بوزون والذي يعطينا فيرميونز. إذا ال L أنا في نظري هنا فيزيكال حقيقي، لكن كل من لا يقاس يعتبر فيزيكال، لكن إذا كان يعني استطعنا أن نقيس في أبعاد صغيرة جدا فإنه يكون فيزيكال. وهذا واضح فإنهم اختاروا هذا الزيرو فيكتور. زيرو فيكتور يعني محتاجين نعرف كلمة زيرو. يعني الآن نتكلم عن أبعاد كبيرة، أبعاد صغيرة. أبعاد صغيرة قد تكون بالنسبة لنا زيرو، ولكن عندما يعني عند الملاحظين القريبين وذوي الأبعاد الصغيرة لن يعتبروه زيرو، وإنما يعتبروه يعني فيكتور عادي وليس زيرو فيكتور. بالتالي تعريف الزيرو مهم جدا في هذا الأمر. وأنا أعتقد أن ال polarization وليس unphysical، وإنما هو physical مثل الاس يعطينا سكيلر ويعطينا سبين زيرو، ال يعطينا سبين هاف، وبالتالي يعطينا فيرميونز، وبالتالي يعتبر ال مثل البوزونات لأنه كومبينيشن يعطينا مثل البوزونات ويعطينا فيرميونات. فال تتعلق مباشرة بنظرية وبالتفاعلات الداخلية التي تجري داخل ذلك الفضاء. الفضاء بالنسبة لنا يعتبر فيزيكال، لأنه لا نستطيع القياس فيه، لكن إذا طورنا أجهزتنا يمكن أن القياس في هذا الفضاء الصغير جدا، ويعتبر بالنسبة لنا فيزيكال ويعتبر إلينا يعني ميجرابل. فلهذا يعني يعتبر فيزيكال، ويعتبر أنه يعني اتمامة الديجريز اوف فريدم. أنا ذكرت أنه في فيديوهات كثيرة أن الخطأ في الجيج فيكسين هو محاولة الإصلاح للجيج اللي هو إنقاص الديجريز اوف فريدم، ولا نحتاج إلى هذا الديجريز اوف فريدم انقاصه، بالرغم من أنه إنقاص الديجريز اوف فريدم يصب في مصلحة الفضاء ثنائي الأبعاد، لأن الفضاء ثنائي الأبعاد أصلا لديه ديجريز اوف فريدم ناقصة، بدلا من رباعي الأبعاد 4 degrees of freedom نحن نتحدث عن 2 degrees of freedom. فبالتالي عندما تعمل على إنقاذ degrees of freedom فهذا يصب في مصلحة الفضاء ثنائي الأبعاد غير المتناظر. لكن يعني للأسف إنه نحن نجد أن الفضاء ثنائي الأبعاد غير المتناظر عندما تأثر عليه بطاقة أو تأثر عليه بكتلة يخرج فضاء رباعي الأبعاد أكثر تناظرا. وبالتالي يعني سنعتبر أن البولاريزيشن بالنسبة للضوء الفور بولاريزيشن هي فيزيكال وهي حقيقة، والفور بولاريزيشن بالنسبة للماسيف اللي هو الدبليو زي أيضا هي حقيقة، بالرغم من أنهما الاثنان يعطينا سكيلر يعتبر سبين زيرو، والسبين زيرو يعتبر حقيقة بالنسبة لنظريتي أنا، لكن لا يمكن قياسها لأن الفضاء صغير جدا جدا وهي تفنى بسرعة عالية ولا يمكن أن نجدها في شكل فري بارتيكل. إذا إنقاص الديجريز اوف فريدم يصب في مصلحة الفضاء الثنائي الأبعاد غير المتناظر، ويمكن أن يعطينا بيانات أكثر في الفضاء الثنائي الأبعاد غير المتناظر، خصوصا إذا تتبعنا هذا الأمر وبحثنا فيه ووجدنا لماذا إنقاص الديجريز اوف فريدم يصب في مصلحة الفضاء ثنائي الأبعاد، وتتبعنا تطور زيادة الديجريز اوف فريدم continuously باستمرار، يعني وبالتالي يعطينا تغيرات إضافية أو بيانات إضافية عن الفضاء الثنائي الأبعاد غير المتناظر. إذن هنا الأمر يعطينا يعني سنجد بيانات إضافية إذا درسنا في هذا الموضوع بطريقة أقوى أو طريقة أكبر وأدق، وحاولنا بدل أن نعمل إصلاح للجيج ندرس الجيج من حيث أنه نجبره أن يكون يعني نزيد الديجريز اوف فريدم وندرس التفاعلات بهذا المنطق وبين هذا المنطلق، بالتالي يعطينا أن كيف يتغير الفضاء ثنائي الأبعاد بالنسبة للفضاء رباعي الأبعاد، وهذا يعطينا بيانات أكبر لهذا الفضاء ثنائي الأبعاد الغريب جدا وغير متناظر. تعالوا نواصل.
And how it behaves. And so let me end the lecture with a few properties. So the first property, scalar product between two physical states. So when I write psi now, it's always an element of this physical space. Scalar product between psi1 and psi2. This scalar product is actually independent of the representative of the equivalence class. Independent of representative of equivalence class. And why is that? Because if you take two different members of the same equivalence class, they will differ by a state of the form a dagger of S times some other state phi. So the difference between two equivalence class members would be such a scalar product. And that scalar product is zero because now the A dagger hits the physical state here, which is annihilated by A, and therefore that is zero. So this shows you that whenever you calculate something which involves the difference of two members of an equivalence class, you get zero. Therefore, the scalar product in our full space is independent of the representative in an equivalence class, and that means that you can now define scalar products of equivalence classes if you define it by the scalar product of representatives. You have an unambiguous and consistent definition. So on our physical space, H physical, we have now defined a scalar product with the usual properties. Okay, and then let me just write down the next point, which is simply a consequence of looking at our examples. Namely, this physical Hilbert space contains only states with positive norm. See examples. Okay, and so then it is really a proper quantum mechanical Hilbert space which gives rise to a quantum theory with the usual interpretation. And there are a few more properties which are important and interesting, so we will look at them on Thursday, and then we will wrap up the whole topic. Okay, so let us stop for today. Thanks, and see you on Thursday.